Last class we looked at limits graphically and saw what it takes for a limit to exist versus for a limit not to exist. Now we're going to look the same idea numerically and then eventually analytically. So we're going to use the graph calculator to develop some ideas. So you will need to get your calculator. So the first thing we're going to do is look at the limit as x approaches 2 of 3x minus 2. So we're going to plug this into the calculator. (3x minus 2). And if we graph this, it should be no surprise. It's a line with a slope of 3 and a y-intercept of 2. What I'm going to do to investigate this numerically is fill in this table of values. And one helpful tool is the table feature. So there's two things here. There's table, which we'll use after we adjust the table set. So you're going to do second table set. Our table is starting at 1.88. This delta means how far are we going up? Well, how far are we going from here to here? 0.04. Then these should both be on auto. Now if I go to the table, all of these values are here and I can fill in our table. So from the calculator we get this table of values, and just like we did graphically, we're going to look at what's happening from the left, what's happening from the right, and then our conclusion. So what can you conclude about the values of 3x minus 2 as x approaches 2 from values just a little smaller, which we already know this notation. We're looking at the limit as x approaches 2 from the negative side. So we're saying as x goes to 2, what's happening there? Well, those values are approaching 4. If we approach from the positive side, those values are approaching 4. So since the limit from the left and the right are the same, they're both 4, the limit exists and is 4. And in fact, what is the value when we plug in 2? We get 4. So we're going to do the same thing with a parabola. So we'll go ahead and put our new graph in here, x squared minus 3x plus 5. Okay, our table set is already good, so I'm just going to go jump to the table and we'll fill in these values. So here's our table of values. So we're looking at what's happening as we approach 2. So as x goes to 2 from the negative side, these are going to 3. From this direction, 3. Since those are the same, the limit exists and is 3. And in fact, when we plug in 2, we get 3. So the conclusion here is if we have just a continuous polynomial, to evaluate the limit, all I have to do is plug the value in that I'm trying to figure out. So the limit of a polynomial function p of x as x approaches c is p of c. So the limit as x approaches 3 of 4x is going to be 4 times 3, or 12. I don't have to graph it. I don't have to make a table of values. I just have to plug it in. The limit as x approaches negative 1 of 17 will be just 17. Here we're going to plug in 2. So we get 3 times 4, which is 12, minus 4, which is 8, minus 1, which gives us 7. And then this one, square root of 2 squared minus 2 times 2 plus 1. So we have 4 minus 4 plus 1, so that's the square root of 1, which is 1. Here we're going to apply the same rules that were on the limits graphically. So if you look at your limits graphically notes, the front cover has these different rules. So we're looking at some generic function f of x and g of x as we go to c. So the limit as x approaches c of f of x plus g of x is just going to be the sum of the two limits. So 3k plus k minus 1. So that's all we're doing here is just adding the given things. Here we're squaring, so the limit of f of x is 3k, so the limit of f of x squared is going to be 3k squared, which will be 9k squared. As x approaches c of 3 times f of x, well, that's going to be 3 times 3k, which will be 9k. And then lastly, the quotient is just going to be the quotient. Okay, and then the rule for composition. So the limit as x approaches 2 of f of g of x is going to be f of the limit as x approaches 2 of g of x. So that's going to be f of the limit as x approaches 2 of 2x minus 1. To evaluate that, we just plug in 2. So 4 minus 1 is 3. And then we plug 3 into f. So we have 3 times 9, which is 27, minus 2, which is 25. So again, I encourage you to pause, try to do this one on your own, and see if you can get it. So this will be g of the limit as x goes to 1 of f of x. So that's going to be g of, we're going to plug 1 into f of x, so 3 times 1 squared minus 2. So that's going to be 3 minus 2, which is 1. So that's going to be 2 times 1 minus 1. 2 minus 1 is 1. So now we're going to look at limits at infinity. So for polynomials going to infinity, we're just going to look at the end behavior that we discussed in the first unit. So for example, this one here is an even degree with a positive leading coefficient. So its graph is just going to look like a polynomial, or a parabola. So as we go to infinity, this is going to infinity. This one is an odd negative, so it's going to look like that. We are interested in infinity, so as we go to infinity, this is going to negative infinity. Here I have an even degree with a negative, so that's going to go facing down in both directions. So as we go to negative infinity, this will be negative infinity. And then as we go to negative infinity, this is an odd positive. So as we go to negative infinity, this graph is going to negative infinity. So now we're going to look at the limits of rational functions. So what's going to happen to a polynomial over a polynomial as we go to infinity. So what we're going to do to come up with some rules is look at some patterns by plugging in bigger and bigger numbers and seeing what's happening numerically. So I am going to use the calculator here. Okay, so we're going to plug in this first one. Rather than doing the stacked fraction, I am just going to put these in parentheses, because if you do it as the fraction, it'll give your answers as a fraction, and we don't really want that right now. Okay, so this is in our y equals. I'm still going to use the table to get these values, but I'm going to change one thing. I'm going to change, I don't care about that for right now. I'm going to go, rather than auto, I'm going to go to ask. So when I go to the table, there's nothing there. But I can plug in these values and get out their y values. So if I plug in 10, we get 4.725. If I plug in 100, we get 49.75. 1,000, 499, and 10,000, we get that. So these numbers, as x is going to infinity, these numbers keep getting bigger and bigger and bigger. So we're going to say this goes to infinity or does not exist. If we're going to infinity, that's not really of value, and limits should technically be of value. So if it's an infinite limit, it sometimes does not exist or undefined. We're going to repeat that with these other three. So I'll have you plug them into your calculator, fill out the table of values so you can see what's happening. So this is what you should have gotten for this function. These values are approaching 0. Now we'll do the next one. So here's what we get for those values. So we get 0.7, 0.52, 0.502, 0.502. So this one appears to be, it's not getting infinitely big or small, it's getting closer and closer to 0.5. Let's do the last one. So here's what you should have gotten for those values. So these ones are pretty clearly headed to the same thing, negative 0.75. So now let's look at why some of these went to a value and some of them didn't. And it's going to depend on the degree. Here, the degree is bigger on the top than the bottom. So the top is going to grow faster, which is why this is going to infinity. Versus this one, which is this one just flipped over, if the denominator is getting bigger and bigger and bigger, these are going to go to 0. These last two, the degree was the same. Degree 2 over degree 2, degree 3 over degree 3. So they basically grow at the same rate. What takes over, where did we get this 1/2? Well, it's the coefficient, that would be a 1 over 2. Because this would be like 1 billion over 2 billion, which is 1/2. Here, the negative 3/4 is where we're getting negative 0.75. So we have 3 cases for rational functions. The first case is if the degree of the numerator is bigger than the degree of the denominator. So if you have big over small, that's just going to grow and grow and grow. So the limit as x goes to infinity of whatever our function is going to be infinity or does not exist. Second case is if the degree of the numerator is less than the degree of the denominator. So essentially small over big. So in this case, the limit as x goes to infinity is going to be 0. Those numbers get smaller and smaller and smaller as the denominator grows. The last case is if the degree are the same. So the degree of the numerator is equal. So they're going to grow at the same rate. So the limit as x goes to infinity is going to be the ratio of the leading coefficients. Okay, so what's ever happening to those leading coefficients, like the negative 3 over 4, is where the limit is going to go. So now we can use those rules to evaluate limits. So here the limit as x goes to infinity, the degree is bigger on the top. So this is just going to get infinitely big or undefined. This one, the degree is bigger here. It's a 1, but 1 is still bigger than 0. So this limit is 0, and we already know that for that graph. That graph is going to go to 0 as we go to infinity. Here, the limit or the degrees are the same. So the limit is going to come from 4 over 2. So 4 divided by 2 is 2. And our last one, the limit as x goes to infinity of 2x minus 5 over 3x plus 8. The degree is again the same. So our limit is going to be 2/3. Okay, so if we look at this table, the table gives values of 3 functions as x is going to 1. Okay, so we have f of x, g of x, and h of x. And what we want to figure out is from the table, which of these have a limit as x approaches 1, which of them, the limit as x approaches 1 is 0. So here's the first thing I'm going to do. I'm going to cross off what happens at 1. I don't care what happens at 1. I only care what happens as x approaches 1. Okay, so if we look at f of x, these values are approaching 0. 0.9, 0.9, 0.9, 0.9, 0.9 is not approaching 0. So this side is going to 0. This side is going to 0.9. So that one is not approaching 0. Even though the function value is 0, the limit is not. Here, we're going 0.9, 0.95, 0.095, 0.009. These numbers are getting smaller and smaller and smaller. On this side, these numbers are getting smaller and smaller and smaller. So they are both going to 0. So again, even though this is undefined, that limit exists and is 0. Here, getting smaller and smaller and smaller. Here, getting smaller and smaller and smaller and smaller. So that one is also approaching 0. So here, g and h both have a limit that is 0. This last example, we have the graphs of f and g, and we're going to find the value of the limit as x approaches 1 of f of g of x. So we're going to have f of the limit as x approaches 1 of g of x. So f of, we're going to use the graph. So the limit as x approaches 1. We have a dot, but the function is approaching 2. So the limit is 2, even though the function value is not. And then f of 2, we go to the graph of f. F of 2 is 3. So there is our answer. So that's how we can do limits from a table of values, so numerically, and we came up with some rules, which is analytically.